Well, today's topic we are covering is network theorems, or can be called as in DC network. Prior to this, uh, last class we have covered up all the network elements. I mean, passive elements and active elements, and we have seen many examples in the case of passive elements as well as active elements. Types of resistors, types of capacitors, then the inductors, transformers. The case of active elements, old diodes, uh, different types of diodes, then transistors, then four-layer devices called thyristors, and integrated chips. These were the examples for the active elements. And now today's class is all about network theorems or DC network. So these are the overview of today's class. Before we understand any kind of network theorem, we should very well know what is Kirchhoffs law, that is current law and voltage law. And we should understand what is mesh as well as loop, node, what is network, active, passive and all. Then we will be covering up the theorems called superposition theorem, Thevenin's theorem, Norton's theorem, maximum transfer theorem, or can be called as a maximum power transfer theorem, and reciprocity theorem. So for each of the theorem, we will take one example, and we will study the current in the branches as well as what is the voltage into that, or what is the current source into that. So before that, we should know what are the few definitions related to network. So what is circuit? A closed path containing a source of EMF and a resistor or an inductor or a capacitor or a combination of two or more these elements is called an electric circuit. Similarly, when a circuit includes a diode, a triode, a transistor, etc., then it is commonly called as an electronic circuit. So this is a general difference between an electric circuit and an electronic circuit. So any semiconductor materials are used into the circuit, then that can be called as an electronic circuit. Last class we have seen active elements. So once again I'm just defining the active elements. The elements which supplies electric energy to the circuit, such as battery, or we have seen an example of thyristor, diode, transistors, and integrated chips are were the examples for the active elements. So the elements which supplies electric energy to the circuit is called as an active elements of the circuit. Passive elements are nothing but the elements of the circuit which receives electrical energy from the active elements like resistors or capacitors, and then converts it into heat or stores it in magnetic or electric field is called passive elements. What is network? We've been saying that network elements, network theorems and all. So when a circuit consists of a number of sources of EMF, resistors or other elements like inductors, capacitors, etc., which are connected in a complicated manner, is known as network. A simple circuit, we say that when an EMF to the circuit is 1, I mean like one EMF is there in the circuit, then that is called a simple electric circuit. But network circuit will be when more than one sources are there, where which the components like resistors or inductors or capacitors connected in little complicated manner, then that can be called as a network circuit. So if the resistance or impedance of a passive circuit elements does not depend upon current voltage, that is the relation between current and voltage involves a constant ratio, then the element is known as linear element. A network with linear circuit elements is called linear network. So that is when the relation between the current and voltage involves a constant ratio, then those circuit or those network can be called as a linear network. When different branches form a closed path in a network is called mesh or loop. We will take the practical example next slide and we can understand more clearly what are mesh. What is node or junction? A terminal point common to two or more branches is called node or junction. Once again, I am repeating, when different branches form a closed path in a network, it is called a mesh. Similarly, a terminal point common to two or more branches is called node or junction. Now, as I said, before we understand the theorems and all, let's have a clear about the Kirchhoffs law. In fact, we have Ohm's law. Ohm's law was nothing but the potential difference across a conductor was directly proportional to the current flowing in the circuit. I mean, V was proportional to I, or we can say that V is equal to I into R, where R is nothing but a resistance which is measured in ohms. But whereas we are saying about the network kind of a circuit, in the network, what is the difference between a network circuit and a normal circuit? In a network circuit, we have two or more EMF sources, two or more energy sources. So whenever a network circuit we have where the sources are more than one, then the Ohm's law is not applicable. That is the only drawback what we have in the case of Ohm's law. So if there are two sources in a circuit, we cannot apply Ohm's law and find any of the parameter, V, voltage or current or resistance, if the other two are given. So let's understand Kirchhoffs law. Kirchhoffs circuit law are two equalities that deal with the conservation of charge and energy in an electrical circuit. What are the two laws? Two laws of Kirchhoffs are as follows: Kirchhoffs current law and Kirchhoffs voltage law. Kirchhoffs current law. This law is also called Kirchhoffs first law, Kirchhoffs point rule, Kirchhoffs junction rule or nodal rule. See, many pronounce scientist name as Kirchhoffs, so it's a noun, so it doesn't make any difference. Somebody says Kirchhoffs or Kirchhoffs. I prefer to call it as in Kirchhoffs law. The principle of conservation of electrical charge implies that at any node or junction in an electrical circuit, the sum of currents flowing into that node is equal to sum of currents flowing out of that node. Or simply, Kirchhoff's first law can be defined as the algebraic sum of currents in a conductors meeting at a point is zero. It means the algebraic sum of all the currents flowing through that particular node or junction is equal to zero. So that is Kirchhoff's first law, or can be called as a current law. Now if you see this, so this we have taken as a node or junction. This point can be called as a node or junction. So this current is flowing towards the junction, whereas this current is flowing away from the junction. This is again away from the junction, and this I3 current is flowing towards the junction. I1 is away, I2 is towards the junction, I4 is away, and I3 is towards the junction. So the current entering any junction is equal to the current leaving that junction. What does that mean? It means all the current, the algebraic sum of all the currents at this particular junction. So in a network, whichever point we take it as a node or junction, at that particular node or junction, all the summation of current, all the currents, summation of all the current should be equal to 0. And how we have taken? We have taken the current which is moving towards the junction is taken as a positive, and the current which is moving away from the junction is taken as a negative. So it means I2 plus I3, because these are the two currents which are flowing towards the junction. So these are positive. So I2 plus I3 minus I1, because it is away from the junction. So minus I1 minus I4 should be equal to 0. That's how we say that the summation of all the currents at a node or junction is equal to 0. And the same equation we can refer it as an I1 plus I4 is equal to I2 plus I3. So this is Kirchhoffs current law, or can be called as in Kirchhoffs first law. This is second law called as in voltage law. Can be called as in Kirchhoffs second law, Kirchhoffs loop or mesh law. That was node or junction law. This is Kirchhoffs loop or mesh law. We have defined clearly what is mesh and what is loop. Mesh is nothing but different branches which forms a closed path is called as a mesh. So the principle of conservation of energy implies that the directed sum of the electrical potential differences voltage around any closed circuit is 0, or the EMFs in any closed loop is equivalent to the sum of potential drops in that loop. We will have a mathematical expression. Now I hope you will understand more clearly. So what the Kirchhoffs law was saying, that if you see this particular equation, the algebraic sum of the products of the resistance of the conductors, right, the currents in them in a closed loop is equal to the total EMF available in that loop. So this you can see that the algebraic sum of the products of the resistance. It means the summation of product of current and resistance in that particular mesh or loop is equal to the total EMF available in that loop. Got it? So we can say that the summation of potential difference, the total difference in that particular mesh or loop should be equal to summation of product of resistance as well as the current in them in a closed loop. So summation of V can be written as summation of I into R. So if you see this kind of a network circuit, so one part of, so this is called a mesh. So this is one mesh, we can address it as in one mesh, because mesh, as I told you, as I defined it, mesh is nothing but what? When a different branches form closed path in a network. Say this is one branch, this is one more branch, this is other one, and this is other one. So different branches, we can say that this is a branch. So we can take this one branch, two branch, three branch, and this is fourth branch. So these four branches formed a closed path. We can see this is a closed path. So this can be called as a mesh or loop. This point B, this point C or D or A, this points A, B, C, D can be called as a node or junction. And this complete path, this is forming a closed mesh or loop. So according to Kirchhoffs voltage law, the sum of all voltages around the loop is equal to 0. It means all the loops. So if you have taken V1 plus V2 plus V3 minus V4 is equal to 0. So the summation of all the voltage around the loop is equal to 0. So at each point, if you address it A, B, C, D, so whatever the voltage we have, that voltage we say the summation is equal to 0. Or because see, this is the total voltage V4. So this total voltage is nothing but V4 should be equal to what? V1 plus V2 plus V3. Or we can say that V1 plus V2 plus V3 minus V4 is equal to 0. This is how the equation comes. Now we have analysis of mesh, how the node analysis are done and how the mesh analysis are done. So the first, let us see how the mesh analysis is done. This is quite important to understand mesh or loop and the node or junction. So mesh analysis is a method that is used to solve planar circuits for the currents at any place in the circuit. Planar circuits are circuits that can be drawn on a plane surface with no wires crossing each other. It means a single branch. So mesh analysis is a method that used to solve planar circuits for the currents at any place in the circuit. Planar circuits are circuits that can be drawn on a plane surface with no wires crossing each other. Mesh analysis works by arbitrarily assigning mesh currents in the essential meshes. An essential mesh is a loop in the circuit that does not contain any other loop. There are certain steps to for determining the mesh currents. The first is assign mesh currents like I1, I2, and up to IN to the n meshes, whatever the number of meshes you have. Current direction need to be same in all meshes, either clockwise or anti-clockwise. So this you have to ensure that the currents, if you have taken in a single mesh in a clockwise direction, so in the all respective meshes, the current should be only in a clockwise direction. So we can take clockwise or anti-clockwise, but it should be same for all the n number of meshes we have in the network circuit. Apply Kirchhoffs voltage law to each of the n meshes. Use Ohm's law to express the voltage in terms of the mesh current. Solve the resulting n simultaneously equation to get the mesh current. So how many networks, how many meshes you have, that many, we need to solve the mesh currents for each of the loop or mesh. Let's take an example. Then, so this is a circuit where which we can say it is a network circuit because we have two sources. This is V1 as well as this is V2. And we can say that how many meshes we have? We have two meshes. Because see, the different branches are forming a closed path. So this is one branch, another branch, another branch, and another branch. So we can say that these different branches have formed a closed path. So we can say that this is one mesh. Done? And we can say that this is another mesh. So this circuit with two meshes, this is mesh 1 and this is mesh 2. And we have taken an impedance R1 and R2 and R3. The current flowing in this particular branch we have taken as an I1. And here it is an I2, the current flowing in this particular branches. And this is I3. And we have taken a node or junction. So this can be called as a node. This point can be called as a node, where different branches are meeting together. So this is A, point B, or C, this is D, E, and F. So this circuit have two energy sources, two meshes, three impedances, and these are the current flowing in each of the branches, and these are the node or junction. So let's see applying the Kirchhoffs voltage law to each mesh. Now applying the Kirchhoffs voltage law. So what was that? It was nothing but summation of product of resistance and current was equal to the total voltage in that particular mesh, isn't it? So if I take the mesh 1, let us apply a Kirchhoffs voltage law for the mesh 1, this one, where which we say that the energy source we have is V1. So what is that? So this includes I1. If I say that the branch, the current in this particular branch is I1, so as we have taken this I1 and here into this particular mesh is an I2, and see both are into the same direction. As the condition says that whatever the n number of meshes we have, the current should be either in clockwise or into anti-clockwise direction for all the meshes. So we have taken as a clockwise here, and so this have to be into the clockwise, the I2 current. So the summation of current and resistance was equal to the total voltage in that particular mesh. That's what the Kirchhoffs voltage law says. So this comes like R1 into I1 plus this is R3 into what? Into this I1 minus I2. This is an I3. So I3 is nothing but what? I1 is flowing towards the junction and I2 is flowing away from the junction. So this is an I3. So I3 is nothing but I1 minus I2 into R3 is equal to V1. Got it? Summation of product of current and impedance is equal to the total summation of voltage in that particular mesh. It means I1 into R1 plus I3 into R3 is equal to V1. Or we can say that I1 into R1 plus I3 is nothing but I1 minus I2 into R3 minus V1 is equal to 0. Now you can see this equation. The same thing we have written. Minus V1 plus R1 I1 plus R3 into this is I3. I3 is nothing but I1 minus I2 is equal to 0. Or if you rearrange in respect of I1 and I2 and V1, so this is nothing but if you take a common R1 plus R3 into I1 minus R3 I2 is equal to V1. Now let's see the applying the Kirchhoffs voltage law to mesh 2. So what is mesh 2? If you see here, this is the mesh 2. So for this particular mesh 2, the equation comes like according to the code Kirchhoffs voltage law. I2, this is an I2 into R2, then same current is flowing through this. So plus R3 into I2 minus this is in a reverse direction. This I1 is into reverse direction because I2 is flowing in this direction from here, and from here. Whereas I1 is flowing in this direction. So minus I1 into R3. Or in bracket we can say that R2 I2 plus V2 plus R3 into I2 minus I1 is equal to 0. Or if you arrange with respect to I1 and I2, so this comes like minus R3 I1 plus R2 plus R3 into I2 is equal to minus V2. We have just transferred this to the right hand side. So this is how in a symmetric way we can write it as, this is for the first equation multiplying I1 and I2. So R1 plus R3 minus R3 and minus R3 by R2 plus R3. This is I1 and I2 should be equal to V1 and minus V2 in a symmetric form. So use I for mesh currents and capital I for a branch currents. So when we see the mesh currents, we have denoted as a small I, whereas the branch current we have taken it as in a capital I. So that's nothing but capital I is equal to small I1, capital I2 is equal to small I2, and I3 is nothing but I1 minus I2. That was all about the mesh analysis. Now let's understand the node or junction analysis. In electric circuit analysis, nodal analysis, node voltage analysis, or the branch current method is a method of determining the voltage between nodes in an electric circuit in the terms of branch currents. So what we are defining or what we are finding out, we are finding out the voltage between the nodes. As we were saying, I can say that this is a node. So the voltage difference between this branch and this branch, between the nodes, what is the voltage towards this particular branch? What is the voltage over here? What is the voltage at this branch, this node or junction? What is the voltage at this node or junction? So if you want to find out the voltage on this particular branches, so then this nodal analysis is to be considered. So there are certain steps to find out the nodal analysis. So this is how we have to find it out, following the steps. All connected wire segments in the circuit. We need to note down all the connected wire segments in the circuit. These are the nodes of nodal analysis. Select one node as a ground reference. So this is most important. First, we have to select complete nodes as a any one of the nodes completely as a ground reference. The choice does not affect the result and is just a matter of convention. Choosing the node with most connections can simplify the analysis. This is just the tricky part. Assign a variable for each node whose voltage is unknown. If the voltage is already known, it is not necessary to assign a variable. So we will analyze, assign saying that V1, V2, V3, because that's all are unknown, and it's in between certain voltages are given. So that need not to be assigned because the voltage value is already over there. For each unknown voltage, form an equation based on Kirchhoffs current law. Basically, add together all currents leaving from the node and mark the sum equal to 0. This we will see into the next slide. More steps like, if there are voltage sources between two unknown voltages, join the two nodes as a supernode. The currents of the two nodes are combined in a single equation and a new equation for the voltage is formed. Solve the system of simultaneous equation for each unknown voltage. Let's see an example how the nodal analysis is done. So this is a circuit. This can be called as a network because we have two sources. Instead of voltage sources, we have taken as in current sources here. Okay. So this is called as a node 1. This is a node 2, and this is a node 3. Done. And here, as per the steps, like we were saying that assigning a variable for each node where the voltage is unknown, like this is unknown, so we have assigned it as in V1, this is in V2, and this is a V3. Then, and these are the resistance value they have given as in 500 ohm, 500 ohm. This is 1 kilo ohm, 500 ohm, and 500 ohm. So we can mark this resistance as an R1. This is R2, R3. Next is R4, and the last one is R5. So the 5 resistance are given. We can say that there are two nodes, 3 nodes, V1, V2, V3, and 2 sources. Okay, so now V1, V2, and V3 are unknown for which we need to solve using Kirchhoffs law. So here the voltages we need to find out using a Kirchhoffs law. So how it can be done? There are few steps which we need to follow up. Choose a reference ground first. As we have talked earlier, we need to choose the reference ground. Okay, so we say that, you know, this node, this complete node, we say this is a ground reference. The underneath whatever we can see, so this nodes, this 3 nodes, or this path, we can say that this is a grounded one. So choose a reference ground node, assign node voltage to other nodes, apply Kirchhoffs law, current law to each node other than the reference node, express currents in terms of voltage notation, solve the resulting system of linear equation of the nodal voltages. So this were the same steps just summarized over here. So let's find out the current and node voltages. So let's see what is at this particular junction. Again, I'm referring this one. So this at particular this junction, what will be the currents as well as the node voltage? So I is nothing but what? V is equal to IR. So I will be equal to V by R. So here at this particular node, we will have an equation because we are finding out a node voltage at particular V1 at particular point A where the node voltage we have assigned as in V1. So here it will be V1 minus V2 divided by What is the value of this resistance? This is an R2. So V1 minus V2 by R2. Or because they have given the value of R2 as a 500 ohm, this comes like V1 minus V2 by 500 ohm. Similarly, on this particular branch, we are asked to find out the nodal voltage. So what is the voltage at this particular node? V1. So V1 by 500. So this branch, it is V1 by 500, and if you take this branch, it is V1 minus V2 divided by this 500. Done? So now you can see the same expression here. This is V1 minus V2 by 500, and this particular this was an horizontal branch for the mesh one, and this is a vertical branch. So this will be here. There was a node with a V1 assigned value. So V1 divided by 500. So what is applying the Kirchhoffs current law at node 1? So what will be the total value? So we are finding out the I1 value. This is an I1. So I1 should be equal to what? This was what? This was nothing but the current in this particular node. Particular branch was V1 minus V2 by 500. This is V1 minus V2 by 500. And here it was nothing but V1 divided by 500. So the total I1 at this particular node will come as V1 minus V2 by 500 plus V1 by 500. This is how simply solving explicitly into the two branches, and this is summing up the two currents in this manner. So this is at node 1. Similarly, let's find out for the node 2 here. So what will be the value? Similarly, to find out for node 2, we have to follow the same steps. So this is a node 2. Let's have V2. So this is V2. This was the node 2, and this was V1, and this is V3. So now we are finding out for the 3 branches, because this is node where which 3 branches are connected. This is one branch, second branch, and third branch. So how we can find it out? The same manner. This will be V2 minus V1 by this was R2. So V2 minus V1 by R2, V2 by R3, and here V2 minus V3 by R4. Isn't it? Again, I'm going to the main diagram. To find out the voltage at this particular node 2, the expression comes like this: V2 minus V1 by this particular ohm value, or this is R2. So V2 minus V1 by R2, V2 by R3. Here it comes like V2 minus V3 by R4. And to sum up, we are finding out the current, because in these 3 branches there is no current source. So if you add up all these values, that should be equal to what? Equal to 0. So this is how, if you find out KCL, apply a KCL at node 2, it comes like V2 minus V1 by 500 ohm plus V2 by 1 kilo ohm plus V2 minus V3 by 500 ohm, and this should be equal to 0, because for this particular node there is no current source directly given. Now the third one, KCL at the node 3. If you see the last one, again I'm going to the reference example, the main diagram. So this is a node 3. So how we can find it out? It's as simple. This comes like, these are the 2 branches. This is the current source. So this will come like V3 minus V2 divided by R4 plus V3 divided by R5, and that should be equal to what? I2. I hope you are very clear with this. So this is a KCL at node 3. I can say that V3 by V2 by 500 plus V3 by 500 should be equal to I2. So this is how the node analysis as well as the mesh analysis are done. So unless you are very thorough with understanding the mesh or loop or the node or junction and the analysis of for mesh as well as analysis for the nodal junction, we cannot understand or we cannot find out the current in any of the branches, or we cannot understand the network theorems. Now let's talk